Here, as it's a classical textbook of the function of coding proteins by the DNA. And it uses words that you would look at and see as digital information words. Information, read, transcribed, translated, language. Okay. I read this stuff and I go, and I'm asking a lot of scholars that are really into this, how does the information in the DNA get read and transcribed? How does it know what to do? Okay. You know what the answer is yet? We don't know. They'll come up with some, well, you've got chemical reactions taking place, and this does this, and this does that. But that doesn't describe anything about how DNA makes proteins. Because I saw a video, and I couldn't find it, how proteins are made within the human cell, and it just absolutely blows your mind. And you're going, what? How does that happen? How does it know to do that? That's what you say. You say to yourself all the time. All right. Now, the function of coding for proteins. Protein molecules are often very large, but that's relative. Very large compared to a molecule of water. And are made up of hundreds to thousands of amino acid units. The 20 amino acids are combined in different ways to make up to 100,000 or so different types of protein in the human body. We have 100,000 different types of proteins that make us work. Okay? Here's an example of what proteins do. Definition of blood clotting is a process of changing from a liquid to a solid, and especially of blood, that is blood coagulation. In vertebrates, blood coagulation result of a cascade series of reactions utilizing 28 different proteins. As I say, sounds simple, doesn't it? I don't think it sounds too simple, but I will say this, that when you cut your finger, it starts bleeding, okay, and you put a Band-Aid. Well, if you just sit there and held your finger without a Band-Aid, it would bleed a long time, but it would eventually stop. Okay. Now, if somebody gets a really terrible injury, they bleed out and die because the bleeding is so severe. But something like a finger will heal without you putting a Band-Aid on it eventually. You're blowing on it. It is. Anyway, the next slide I'm going to show you is a detailed definition of what happens when you cut yourself and your blood coagulates. Okay. I'm not going to read them all because it's very, very long, very involved, but it's all there. And if you want, I'll print this out in a Word document and send it to you on the email if you want to see this. But this came out of Michael Behe's book, Darwin's Black Box. Just to get started, I'd say a cut occurs in Hagman factor. All these names are names of proteins or enzymes, okay? Hagman factor sticks to the surface of cells near around the wound. Bound Hagman factor reacts with another enzyme called HMK to produce activated Hagman. Kallikrein reacts with activated Hagman to produce kallikrein. Hagman factor also reacts with HMK and kallikrein to form activated Hagman. Now, this is the beginning of what they call the cascade. That's what the proteins do to each other. As you go down through this, you realize there's even proteins that come in and cut another protein in half. Okay, they do all kinds of stuff. It just follows the mind about what's happening to your blood. At the end it says when fibrin, which is the major protein that forms a web that actually physically stops the blood cell from coming through. It makes the opening so small blood cells can't get through. That's how it works. When fibrin reacts with activated FSF, many more cross ties are made with other fibrin filaments to form a more effective clot. So that's what happens when the clot forms. Once the clot has formed, the bleeding is stopped, and the body is healed, so there's no opening again. This is what happens. Blah, blah, yada, yada. What I'm saying is that there's a whole new system that kicks in to remove the clot, to break it down and put it back in the bloodstream. Okay. Do y'all have an understanding of how that happens?
I got it.
You got it figured out?
I got it.
All right. As you look at all this and read it, a logical question is, how do we know that we have to be able to produce the whole set of enzymes or factors in the clotting cascade in order to successfully accomplish the procedure? All right, now, without reading the last one yet, what I'm saying is that in the bloodstream are all these proteins. It's floating around the bloodstream all the time, looking for a cut or a breach in the system. When that happens, they go to work. It's almost like they have a little computer in them, and a mind will run on them. Oh, there's a bleed. Let's fix it. I mean, even though, if somebody even said to me, well, I can explain to you how that happened by evolution, I still can't put my mind around how it happens, period. Whether it happened by evolution or just by some design. I still can't figure that out. If anybody can, be glad to hear about it. Could this have evolved one random step at a time, which is what Darwinian evolution says? Each step in this process depends on the prior process for blood clotting to work. If a step does not happen, blood clotting does not happen, and I guess if blood clotting doesn't happen, you bleed to death. Okay, people do bleed to death, but I mean, even with a cut to your finger, you would bleed to death. How could that happen? How could that happen over billions of years, little changes at a time? All the changes that were taking place, you still be bleeding to death. That's the statistics of things like blood clotting and evolution. Another function is DNA replication. Replication, yes, thank you. DNA replication is vital for a virtual endless list of functions, from reproduction to maintenance and growth of cells, tissues, and body systems. To copy itself, a DNA molecule essentially unzips. Now, again, you can see the structure here. It unzips in the middle along those nucleotides. There is a protein that actually does that. It goes alongside it and cuts it in half when it's ready to be duplicated. Thus resulting in a series of bases without pairs. It means that these nucleotides are now free. There's an active part they want to combine with something, like chemically combine with something. As the nucleotides connect with unpaired bases on the backbone of the DNA molecule, they build a new strand that complements or matches the other sequence. The end result is a strand that is a perfect match to the original one prior to unzipping. Cells in your body replicate for purposes such as making new skin or blood cells. When mistakes occur, and they do, it's called mutations, there are repair systems in place to remedy the mistake, or alternatively, a cell has a marker for destruction. Sounds like a little manufacturing plant of some sort, but that's what happens when DNA is replicates itself. Okay. Genetic code. DNA is important in terms of our genetic code, in the sense that it transfers genetic messages to all the cells in your body. Remember, we had this, open the floor for discussion. How many cells do most people have in their body?
I got about 8 billion.
You got 8 what? 8 billion? Okay, anybody else?
3.8.
8 trillion?
No.
Trillions. You got a number?
2 trillion.
2 trillion. Okay, anybody else? Well, they don't know exactly, but it's between 37 and 100 trillion. I bet I have 100. At least. All right. And it's interesting to me they don't know. I'm trying to figure. I heard another interesting fact that has nothing to do with this. There's more bacteria cells in your body than there are human cells. And the bacteria in your body do things for you. And they've got more than 100 trillion bacteria cells. They're a little smaller than human cells. A lot smaller. Anyway, if you think